So in this sort of case where we put the prior on the intercept, this sort of example of this missing value, we sample a C from a Gaussian with some variance given by alpha, perhaps. Then we use this very complicated rule that involves summing efficiently. The likelihood here, that's what we had before, P of y given C. So we're just, I mean, obviously it's conditioned on M and variance, other stuff, but just to try and keep it clean, I'm showing you the thing we're doing inference over. And then we find this posterior. And then what we do is we work with the posterior parameter in the model. So we say, actually, I'm going to use this distribution over parameters to make my prediction. Now, I like this picture because I think it highlights exactly what goes on and how complex a process this is. So this is our prior over an intercept, which would be the prior over a location parameter. So the example Laplace did in his 1774 paper, he actually used a sort of uniform prior, I think, and he used this exponential likelihood, and he was looking at the location parameter, which is like C. So he didn't have an mx, he just had a C. So he's looking at the mean of it's the location parameter for the exponential. So you've got this prior over what you think it is, and then Bayesian inference is just a minor argument between a prior and a likelihood. Now, the likelihood is not a probability distribution on this scale. So this input, unfortunately, hidden behind this E is a C. So this input here is C. So the prior is a probability distribution in C. The likelihood is not a probability distribution in C. It looks like it is here because the likelihood happens to be Gaussian. But if we were looking at a logistic regression, what we would see is like a sigmoidal shape or something like that. And if we were looking in a multidimensional system, we would see this is a Gaussian tube. Yeah, it's not dropping down, it's only like a Gaussian tunnel. So it's not normalized in C, because obviously it's not a probability distribution in C, so it doesn't need to be. It's a function of C. So the likelihood is a function of the parameters, not a probability distribution, but it's a probability distribution over Y. And Bayesian inference is just a little argument between these two. That a priori you're saying, I have this belief in what the parameter was, and then your data comes along. This is one data observation leads to one Gaussian bump. If you had many data, you would be basically multiplying many of them together. So in Bayesian inference with many data, you would have another Gaussian here, and they would all be arguing about what the parameter is. So it's just the product of these two, because that's the product rule. That gives us the joint distribution. Yeah? So that's this region here. So the joint distribution is given by multiplying this by this, which gives us this region here. But we then need to divide by something to make it a probability distribution in C. Renormalize. So we get that. So that's the probability, that's the sum rule is applied to that joint distribution. So it's the product of those two renormalized. So the nice thing about Gaussians, and why I kind of work on Gaussian processes, is because Gaussians combine together to become Gaussian. And they're very, very unusual. So when I was at school, I always thought that Gaussian was the most boring of probability distributions. Well, even university, quite a long time. And that's because it does seem that way. And particularly when they make you look up those tables of things, which they probably don't do anymore, but of standard deviations and stuff like that. You have to compute the mean of, you were good at maths, and then some part of maths was that you had to sum a load of numbers, and then that was one answer, and then you had to do some reasonably weird formula to compute a variance, and then square root it, and looking up something in a table, and you were getting points for that. So you were like, oof, can't we do something complicated? So I hated that, and so I always thought, well, I hate everything to do with Gaussians. But actually, they turn out to be really interesting when they get multivariate. And they also have all these weird properties that they didn't tell us about, which is things like when you multiply two Gaussians together, the result is Gaussian. And the reason for that is because Gaussians have this exponentiated quadratic form. So you've got a prior, which is of the form of a quadratic, the quadratic being a function of C, and a posterior, and a likelihood that's a form of a quadratic, the quadratic being a function of C. And when you multiply the two together, you get another quadratic, because multiplication just leads to the sum in the top there. That's kind of a weird property. If you do it with two Laplacians, it doesn't work, because the sum of two absolute values doesn't give you a Laplacian again. You start getting these weird, in fact, it doesn't work with student t's either. So if you multiply two student t's together, you don't actually get a joint student t distribution. You get something different, something that's widely used in ICA. Now, this means as well, so there's this trick here, which I think if you don't have like a supervisor that knows probabilistic modeling or something, you probably don't get taught this trick. And I have no idea where it's written down. So it's like maybe it's a secret trick, or maybe it isn't, maybe everyone knows it. But what you do when you do this process of Bayesian inference is you just multiply these two together. And if you're in this family of exponential models, this conjugate exponential family, which is where you can do this sort of stuff quite simply, you always get something on the right side that you can recognize as a distribution. That's kind of, to me, the loose definition of a conjugate exponential family. You end up with something, so you start with a likelihood, you combine it with a prior, and on the right-hand side, you end up with something that is in the same family as your prior, which this is here. So it's even more special case because the likelihood's in the same family as well. Most conjugate families, which you hear about, don't have the same form for the likelihood and the prior. But in the Gaussian conjugate pair, you get this sort of thing where you recognize the posterior as the same functional form as your prior. And once you've recognized what distribution it is, the really cool bit is you don't even need to do that integral. You can just write down the form of the Gaussian. So how does that work in our case? Well, this is what those two distributions look like. I will always use linear algebra. Philip Hennig pointed this out at the last Gaussian process summer school we had, which I thought was a really nice way of thinking about it. Linear algebra is pretty much every linear algebraic operation corresponds to some inference in a Gaussian system. So, you know, matrix multiplication, all this sort of stuff has a corresponding meaning in a Gaussian system. And computers are pretty good at linear algebra. So even if you don't like them as models, we're left with a world where they're one of the few models where computers are pretty good at doing inference in those systems because it's all based on linear algebra. And so that's why we tend to definitely always use matrices. So using the matrix writing as the inner product. And we have these sort of forms here. This is our likelihood now, where our function is, this could be phi of x, or it could be a multivariate input. It doesn't matter. And we want to combine it with this prior. So the trick when you're doing these things is to try and get this thing. You don't bother writing down the integral. You write that is proportional to that, if it's a conjugate pairing. Michael Betancourt is here, and he's going to talk about Stan later on, and that's really when you don't have these simple models that I'm dealing with. This one way of trying to do the inference, which is really useful, but this is in the case where you can do the thing tractably, which is quite often if you use simple models. And what you do is you actually complete the square. So you look at the log of this posterior. Now, because these two are products and these two inside is sum, the log of the posterior is just the log of the, that's just the likelihood multiplied out, and then that's just the term from the prior. And now you recognize by inspection what the covariance must be. So what you now have is you know that you've got this constant term, but you care only about the distribution over W. So the true distribution is e to the power of this times e to the constant. But you ignore the constant because you say, well, this thing's just a quadratic. So I just have to rewrite this in a form that looks like a Gaussian form. And that's a multivariate Gaussian form. So there's a little odd cheat here because neither of these is actually a proper multivariate Gaussian. They're just products. So why? Because their covariances are the identity. So this thing, that sum, can be pulled out the front here to a product, so it's independent across y. And this thing here, W transpose W, can of course be written as sum of Wi squared, where I is the element there. So sum I equals 1 to, what am I using for P? So where P is the dimensionality of your data. Oh, look at that, that's really clever, look. Oh, nice, I like that. So that's equal to that. And then, of course, once we've got the sum in there, we can pull that out to be a product out here. P equals 1 to, I equals 1 to P, and then replace that with Wi squared. So it's an independent Gaussian again, yeah? So it looks like it's something funny, but it's just an independent Gaussian. But the cool thing is, so in this case, we're sort of saying independent prior distribution over the weights on this system. But what's going to happen when we multiply these things together is things are going to correlate in the posterior. So the reason they're going to do that is because I can't reach that one up there and draw on him, but that one up there, oh, look at this. Missed slightly. That term there, W is appearing as an inner product, and when we try and get the new distribution in W, that's not a distribution over W, so it's not causing any correlation there, But when we try and do the posterior distribution over W, we're going to find that X gives us the covariance of W. X determines what the covariance in the posterior is because of that inner product there. So that's how things end up correlating. Okay, so, but to do that, we multiply out like this, and then we're going to collect the terms. So we have this term in W, which is a quadratic form, yeah? And this term in W, which is a quadratic form. But we don't quite want them in that form. What we're going to do is, I'm just now looking at this term here. What we're going to try and do is identify what must be the inverse covariance. Because the form of the Gaussian distribution here should be W minus mu C minus 1. This is the form of a multivariate Gaussian. So we're looking to convert that guy to this form. So we're looking for a term that will look like W transpose C minus 1 W inside there, and that will be our inverse covariance. So multiplying, well, separating the two terms that involve the W quadratic as this one, and so we just have to rewrite that in such a way that, well, first of all, I like to go matrix form with the data itself. So this is just pulling this sum inside here. The sum, this is like the covariance. It's not quite the covariance because we're not mean subtracting, but it's kind of like the covariance of the input data. And that can be rewritten in this sort of matrix form, X transpose X, which I prefer. So in this system, X is a design matrix. Now, there's lots of traditions for using design matrices in machine learning. And I think the right one is to do what the statisticians did. It's kind of like driving on the left or the right. You just follow the convention. So left was the first convention, so that's the side you drive on. You don't make up a new side like in the middle of it all and say, let's drive on the right. Just like that, you don't suddenly decide that your data. So you've got two ways of writing a data matrix. So the data inputs by convention in a matrix of size n by p. I also use p because that's what the statisticians use. So in other words, your data inputs under this thing are in a sort of x1 transpose, x2 transpose in the way that we were writing x before. Now, some people don't like it because they think, well, if my data inputs are little vectors x, then they should line up that way. So it should be p by n. Well, but it doesn't matter which way. I mean, there's a convention. Someone else came up with it, and it helps. We don't crash with each other if we use that. So I prefer this design matrix convention. So of course that means once you have a convention, stick to it, and that will help you do things. Like it'll help you notice that, well, let's see if I can do that again. That guy there is a p by p matrix, yeah? So he's not n by n, he's p by p because he's an n by p transposed by n by p, which means he's p by p. So that's the right size for that to be correct. But if we define this design matrix the other way, that guy there would be equal to x transpose, which is, in our case, it's an n by n. So it's just a matter of definition, but I just want to emphasize that I'm using that definition. And then once I've got that, I can recognize this object here. I pull a I to the times alpha to the minus 1 out and realize that that's my covariance. So that's the covariance of the posterior because this is the only quadratic term. And when you multiply out this guy, W C minus 1 W, that tells me, sorry, I should have said inverse covariance, the precision matrix, that tells me that there's only one term involving W transpose W, and that term has C minus 1 in the middle, so that must be C minus 1. So that's the covariance. And then you can proceed, once you've got the covariance, you proceed to complete the square of the system, and you recover that the mean has this form. So it looks like the covariance, it's arising from this guy here, which is the only linear term now with W in it. But when you multiply everything out, the linear term also needs a C minus 1 in it. And that's not there. So in order to get that C minus 1 in, you have to put a sort of CW in, the mean, to cancel the C minus 1. So that appears there, and you get the covariance times X transpose. So that gives us our posterior. But I'm kind of a bit less interested sometimes in the posterior. I'm interested in the predictions. We've become very obsessed with the posterior, again, I think, because people have worried a lot about the parameters. But if you're only And you might be worried about the parameters, and if you are, it's very informative to look at the posterior. But let's say you're not worried about the parameters, you're just worried about predicting on a future test data. So now y star is some future test point I'm going to be given, and x star is its location. And I'm interested in the probability of y star, the probability distribution of y star given this new location. And now, this to me is the fundamental object actually. This is just an intermediary. This object here is the probability of y star given the test input and the training data, x and y. But it's found by integrating the likelihood of the new point, which is just the same as the likelihood as the previous points, under this posterior distribution, P of y, the one we've just computed. So since these are both Gaussian, this is also Gaussian, just in the same way, because it's the multiplication of two exponentiated quadratics, and then it's integrating one out, which also leaves everything Gaussian. So there's this weird situation for these models when things are Gaussian, where everything's Gaussian. So this guy's Gaussian. Well, if this guy's Gaussian, then so is this one and this one. It's always the case. So you constantly sort of stay in the Gaussian family. And that's not always the case with probabilistic modeling, obviously, but it's very convenient that it happens. Now, an interesting point about this is we didn't go through the maximum likelihood solution, but if we were to just maximize the likelihood of the linear regression, this is what we'd have recovered. This is the maximum likelihood solution. Now, I've expanded about the mean of the posterior here, and you see this similarity between them. We've got this extra parameter arising from the prior. If we set that value there to be the variance of the prior to be infinity, then this 1 over variance would be 0, and then this would cancel with this, and then we'd recover this. But it wouldn't be a valid prior distribution because it would be infinite variance. So it's not a proper prior distribution. But that's kind of how Laplace and Gauss would think about generating maximum likelihood, by making that assumption, and then they would have these solutions, these point solutions. So they were sort of approximations to the full Bayesian things. But as I understand it, they justified these things by taking the Bayesian explanation as to why one should do it. But they effectively would then do maximum likelihood to estimate the parameters. So there's this duality, but what this means is in this case, so this is problematic. Remember I said that this is a P by P matrix. Yeah? So when are we going to not be able to do this inverse? There's a situation when we can't do this inverse. It's not full rank, yeah. So if n is smaller than p, the matrix isn't full rank. Or if there's multiple repeated data points or whatever in n. We can get a non-full rank matrix here, and we can't do this inverse. Sorry, there's an I missing there beside alpha. Damn. There should be an I in here. So if this matrix is always full rank, because this should be alpha times I. I think it was it correct here? No, it's missing there as well. Terrible. It's there, that I. It should be there and should be there. So that forces this matrix to be full rank. So it's always invertible as long as alpha is not infinity. That's reflecting the fact that it doesn't matter how many data you have, you can still make a Bayesian prediction. Even if your data is 0, in the case where you've got no data, this guy here becomes 0, and this guy here is just the inverse of the prior. It's just the variance of the inverse prior being inverted, so you're just taking the expectation under the prior distribution. So even with no data, you can still make a prediction, and the prediction is your prior distribution. And you might think, is the one under your prior distribution. And you might think, well, that shows how important the prior is, and that's why people think it's so important. But I want to sort of present a slightly different view, that if you do the marginalization of W to get the marginal likelihood, so remember going all the way back to Bayes' equation, this object here I haven't talked much about, but it's the one that gives us the marginal likelihood. It's the probability of the data with those parameters removed. Well, my argument would be is that's the new likelihood, right? So but you could start with that. So let's look at that for this case. I mean that's the real model. It's the new likelihood. I don't really like the term so much, likelihood. That's the model we're interested in. So we can actually compute the marginal likelihood in that case, and it has this form. Now, I want to spend a little time looking at that form, because in that form, what dimensionality... Ooh, that's a nasty eraser. That's slightly better. So we defined earlier, we've got x is in the reals of n by p. So what size does that make x transpose? N by n, yeah. So x transpose is a matrix of n by n. So what's this guy saying about y? Is y independent now? This object here is doing what to y? It's forcing correlation, isn't it? It's forcing a particular type of correlation, which actually means that y will always be linearly related. This, if we do the Bayesian model, this is our real assumption about y. And it arises directly from the properties of multivariate Gaussian distributions, that this should be the assumption. You don't even have to do the complicated integrals when you're doing Gaussian processes. They're kind of all trivial. So I'm sort of smoothly moving into Gaussian processes. So normally this integral is intractable, and so I've already said, so you've got Michael Betancourt and Mark Girolami. We'll be talking about MCMC and Stan. If we were there yesterday, we had Harvard Rouet to try and get this object. But by staying in the world of Gaussianity, I'm sort of moving more into my own domain where you can actually often write down the marginal likelihood directly. And this is the thing you should think about. So you shouldn't have people complaining about your prior. You should have people complaining about your model. And this is the model. This is what the model says. So what does this model say? This model says that if you look at the marginal of this, so this is a covariance matrix now. And the diagonal of this covariance matrix will be of the form x1 transpose x1, x2 transpose x2, x3 transpose x3, so on and so forth. And the off diagonal will be x1 transpose x2, so on. Now, if it was one-dimensional input, this would be x1 squared, x2 squared, x3 squared. And this is the variance. This is a covariance matrix, so this is the variance. So it's basically saying that before you start, you're expecting a variance which goes up quadratically. So your standard deviation should go up linearly. So it's no surprise because this is a linear model. Yeah? So this is your prior, but you're also saying, and the thing that arises from the choice of variance on the prior is you're making a statement about the overall scale of this thing. Yeah? So we had a prior over, so originally we had a prior over C, but then in the multivariate case, we had a prior over W, which is these coefficients, which is alpha. And that tells us what the scale of this function is. So in this sort of model here, or what the scale of this gradient is, sorry, because the scale just goes up, obviously. So in this object here, we have this one thing that's determining the sort of scale of this gradient, and then one thing that is determining the noise. So we're adding that to the noise. Now, this can be seen as two different processes because the sum of two Gaussians is always Gaussian, with the result being the sum of two covariances. So this is a really important formalism in additive models. Now, of course, we did that for x, but we said earlier that we could use basis sets. And if we use a basis set, this is phi transpose. So we have a lot of control over this object here. We can put our basis functions in here, and then we get the covariance out. Now, there are definitely merits to thinking about it in the prior likelihood way. That's one way of thinking about it. But this is a different way of thinking about it, which is very, very powerful. And it's the way of thinking about it that people use in Gaussian processes. And they're kind of increasingly popular. And they map onto kernel methods. So another way of viewing this object is as a kernel. So if you were to kernelize this distribution here, you also end up with a Gaussian process. So it's like a kernelized linear regression. But in Gaussian processes, we don't really have that interpretation. We take the interpretation directly that the kernel is like a covariance. And then this makes us quite able to construct quite powerful models by adding these covariances together. So this Gaussian is no longer IID across the data, and that's where things get interesting. The Gaussian that we had to learn at high school or whatever, that's boring. That's a tedious Gaussian that we don't like. We like the Gaussians when they get multivariate. That's when they get really cool. So let's just sort of go one little sort of review of how you can think of a multivariate Gaussian. So one easy way to try and go multivariate Gaussian is just to take two variables and sample them independently as Gaussian. So if we've got two variables, height and weight, and we say they're both Gaussian distributed, then we can just sample one and then the other, and then we can plot one against the other. So we're independently sampling P of W, P of H. So this means that our joint distribution is P of W times P of H. But because they're both quadratic, P of W and P of H, so it's just multiplying P of W times P of H to get this thing here, which will also be Gaussian because it's the multiplication of two exponentiated quadratics. That's not true for other distributions. It doesn't happen like this. But in the Gaussian case, multiplying two independent things also gives you a Gaussian. But it gives you this sort of particular structure which I'd call axis aligned. You can only have variance in these two directions. Because if you have anything off that, then you've got some sort of conditioning. Then one's dependent on the other. So we can do that, but we can't specify any relationship between height and weight. We're just specifying this independence. So of course, in reality, height and weight are correlated. I weigh 85 kilograms, but I'm not very large, but that's because I'm tall, because height and weight are correlated. They're not correlated in this way, though, really, are they? But anyway, that's the body mass index that people use to describe that correlation. So we can think of, in practice, you have to sample height, and then condition on height, you sample weight, or vice versa. You know, if you know the height, then you know something more about the weight. And this gives you this correlation. Yeah? And I like to introduce multivariate Gaussians in this way because thinking about this correlation and how you could recover this correlation, I feel gives you a lot of sense about what's going on in a covariance matrix. So independent Gaussians are like this. And if you take the multiplication of two independent Gaussians, you get this form, these quadratics again appearing in the top. But we like to write that in matrix form, which using the same trick of before is taking out these two sigma squareds and making a matrix in the middle. It's a diagonal matrix. If it's a diagonal covariance, they're not obviously uncorrelated. And I've also moved the mu's in. So I've stacked W and H as a little vector, subtract the mu's, and if you do these matrix multiplications, you just recovered that. So this is the standard independent Gaussian where we've got a diagonal covariance where these could be on different scales, but nothing more than that. Now this is, to me, the fundamental object, because you can always rotate back to this. So the idea of, and this is diagonalization of a matrix. All linear algebra operations map back to something in a Gaussian, some operation in a Gaussian. And this one's is diagonalization. So if we rotate y, so now if we just rotate the inputs, we can bring this rotation out of there and put it either side of this diagonal. So I always think of a covariance matrix like this, which is just like I start with that Gaussian from before. Oh, that was the, was that the, no, that was the, no. I start with a potentially this independent Gaussian, which is axis aligned in some way. So this is weight and height, and they can be scaled however you like, because it'd be weight in kilograms, height in meters, weight in stone, height in kilometers, whatever. But then I rotate that. I rotate the input, and I end up with something like that causes these things to be correlated. And that's the only operation I need to do on the independent system. And that's what I'm introducing here. So all Gaussians are just that. There's some directions which have then been rotated to give us the correlation. Very simple operations. So that's all they're expressing is correlations. But those correlations are really important. So I think of the covariance as this. Now that also, as we'll hopefully come to if I've got time, maps onto the eigendecomposition of the covariance matrix as well. Which is why PCA is such a sort of fundamental thing. Because when you do PCA on a covariance, you're recovering this structure. You're diagonalizing it. So PCA is finding these original bases in which the directions were uncorrelated. But they have some cool properties, cool properties, which are very exceptional. and this is why Gaussian processes, you see them all the time and you don't see other processes so much. Sums of Gaussian variables are also Gaussian. So if I add a bunch of y's together, and they're each Gaussian distributed, the new variable is Gaussian distributed with the sum of the means and the sum of the variances. Now that's really, when you first get told that, like at school or whatever, you think, yeah, whatever, fine, that makes sense. You add two things together, they're still the same thing. But that's amazing. No one else does that. And in fact, everyone else goes towards a Gaussian. Anything else, central limit theorem, as long as they're finite variance, if we add two things together, they tend to be a Gaussian. So other distributions tend towards this, which is another why Gaussian processes are quite fundamental, because if you've got any process where lots of things are happening, and you're just seeing the sum of all those things added up, then that's going to be Gaussian as well. Now, that's dangerous too, because if you're really stupid, after you've finished your PhD or whatever in machine learning, you'll go and work in a bank. And then you won't realize that while that is true for some of the time, every so often, Russian debt defaults or Argentinian debt defaults or large-scale mortgage payment refailures, they don't occur in small little ways being added together. A Gaussian process is a perfect model of the financial world as long as you only sample the financial world every 200 years or so. Because on that scale, you do get these massive big effects, but they will all add together again to look like they're Gaussian. But if you're in the middle of one of those effects, things will be non-Gaussian. And a lot of models in finance are based on stochastic differential equation models which have Gaussian assumptions underneath them. And that apparently they don't learn because that's caused problems a couple of times. But there are many situations where you do get a sort of Gaussian effect. Scaling a Gaussian also leads to a Gaussian. So if I just multiply a Gaussian by a fixed number, then I also get a Gaussian. Now that's really nice because those are the two fundamental operations under linear algebra. And then that leads to this thing, which says, and this is linear regression now. So what we're going to do next is, in fact I've got it the wrong way around. I've drawn x from, so I'll do it on the board in a second. If x is drawn from a Gaussian with mean mu and variance, covariance sigma, and then y is related to x through a matrix W, that's just a series of scalings and additions of x. Then we know that y is drawn as a Gaussian with a mean given by W mu and a covariance given by W sigma W transpose. That's actually exactly what we just did for linear regression. So let me derive the marginal likelihood for linear regression using only that rule. It's very cool how much stuff you can do with Gaussians now, because normally you'd have to do a load of integration. But once you've proven that, so we're saying in linear regression, we said what? W is sampled from a Gaussian with 0 mean and covariance alpha I. And then we said that y is equal to W transpose x. Well, in fact, let's write it in matrix form. So I write it as x W, have I got that right? That's n by p, that's p by 1. That gives me an n by 1. N by p times p by 1 gives me an n by 1 for y, plus I'm going to have a vector of noise epsilon, and I'm going to say epsilon is drawn from a Gaussian with a standard with a variance sigma squared. I applied that rule on the right. That tells me that y must be given by x times alpha minus 1I times x transpose. That's this rule here. Yeah, for the covariance, the mean of W is 0, so the mean of y will also be 0. But it's not just that, because I'm adding this other Gaussian. And adding two Gaussians just makes me add the covariance plus I sigma squared. Yeah? Now, if I pull the alpha minus 1 to the front, that was the covariance of the marginal likelihood of the linear regression. Yeah? Pretty quick to compute under that rule. So if you have these Gaussian systems and these matrix systems, these things turn out really simple. So that's why I didn't bother computing the marginal likelihood before, because given these two rules, given this rule basically, you can compute the marginal likelihood. Now, probabilistic principal component analysis is an algorithm that Mike Tipping and Chris Bishop came up with when I was sort of at Aston, and it was almost the same model, only x was sampled from this system, and we would tend to write, just for convenience, we tend to write this Wx. In this case, y is multivariate. And in that case, it turns out the covariance is W transpose plus I sigma squared, just applying the same rule. This is why you see these patterns emerging. When you do this for real, like if you try and do the integral and everything, you have to go into a big expansion of the matrix inversion lemma and move all these terms around and so on and so forth. And then you just collapse it all back down. It's like, oh, that came out really simple. That's how I was doing it for quite some years. And the reason it comes out really simple is because of this. They're very, very simple, these Gaussian systems. And that's what Philip said was totally correct, that it's all just linear algebra, because the linear algebra just pops through into the form of the covariance. Kalman filters, it's all the same thing. The same thing's going on in a Kalman filter, which is a linear Gaussian system. And Kalman filters are special cases of Gaussian processes. So what goes on in a Gaussian process? What does it mean to have this weird prior of correlated things? Well, what I want to do now is show you a sample from a Gaussian of that form. So you have to remember when you're doing a Gaussian process that this is one sample from a 25-dimensional Gaussian in this case. I've chosen it to be 25-dimensional. So in other words, I've got 25 data points. And I'm specifying not the XX transpose covariance. We'll look at what that looks like later. I'm specifying a different covariance form. And I want you to forget X even exists and just look at this object here, which is the covariance I used to sample from. So you can do this when I show you the form of the covariance. You can do this very easily in Octave or Python or whatever. This form here is saying that each point has a covariance of 1. Has a variance of 1. And because it's 1 down the diagonal, this matrix also in this case has an interpretation as a correlation. So I've plotted the sample I took against its index, and I'm showing the covariance against its index. So points 1 and 2 are highly correlated under this model. And they're highly correlated here. In fact, all neighboring points are highly correlated. Now, I think the weird thing about doing this is if you sample from a Gaussian, you'd sort of expect probably to see a very nasty discontinuity, noisy thing, right? But what we're seeing here is also some sort of weird, smooth structure. And in fact, you can show that this is infinitely smooth. Exactly the opposite of what you expect to get out of a Gaussian. And it's infinitely smooth because of this correlation structure and the way it degrades. So if you get over here, point 25 has 0 correlation with point 1. It actually has a really, 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 really small correlation. But so small it's below computer precision. And if you've got this point here, point 5 has a sort of weak correlation. It's sort of 50% correlated. Hey, Joshua. 50% correlated. Joshua's cleverly finding out where the venue is before he gives his talk. Some of us prefer to sustain the uncertainty as long as possible and ask the hotel receptionist, how do I get to the university? And when the hotel receptionist doesn't reveal there's 5 universities in Reykjavik and just says, you can walk, it's a lovely day. And I thought, she's right, it is a lovely day. So I then inferred she'd be right about other stuff. So I believed that when she circled the bit of paper that she was identifying the correct university. She wasn't. OK. So we've got this correlation between these things. And what we can do is one of the properties of another fantastic property of a Gaussian, which I haven't mentioned yet, is that if we want to look at the marginal distribution of 2 points, it's very easy. That is another nasty integration, right? We're integrating out 23 things, 23 dimensions. We're going to do it in summing, but it's that fancy sort of summing that we use that big long S for, that Leibniz and Newton contemporaneously came up with, integration. So we need to integrate over these variables, but in a Gaussian, that's just amazing, because it just involves putting your hands over all the parts of the covariance apart from those 2 tops. That's why correlation is so fundamental. If that weren't the case, and it isn't the case for most other distributions, it's a very odd property. The correlation does not change when you integrate out all these other points here. And if that weren't the case, then we could never quote correlation about a data set and find it meaningful. because the correlation would depend on having measured other things, yeah? It doesn't depend on how we've measured other things. It stays the same. The covariance and the correlation stay the same. So integration over all these guys is very easy. And you know, you're going to hear a load of lectures about how you do that in other distributions. It's very, very hard. But Gaussians, it's very easy. So we just get rid of all those guys, and we're left with the marginal probability of these 2 points. And just instantiate the values we've used here. We've got very strong correlation, and I'm drawing it with one contour here. And now we can talk about conditioning. Now, I think that inference is just conditioning. I want to get out of this idea that it's learning parameters, IID, blah, blah, blah. I believe that you have a joint distribution over your data set, and when you want to make a prediction, you condition on your training data, and you predict your test data. We saw that formula before. I took it as the expectation of the likelihood under the posterior of the parameters, yeah? And I think that's how we should think about it. Pretty much anything else is a special case of that. That's the most general thing. Maybe there's people that object to that, but that's how I think about it. So this is the joint distribution, and now we're going to do a very difficult challenge. We're going to deal with one training data and one test data under this joint distribution. So I'm going to make an observation of F1. The F1 is minus 0.313, which is actually what it was on the previous slide. And conditioning on that, I now want to make a prediction of F2. Now, in the Gaussian case, again, crazy property, all the conditionals are Gaussian as well. So the previous property is it's closed under marginalization. It's also closed under conditioning. It has to be, if you think about it, because the way to get a Gaussian is to multiply a Gaussian by a Gaussian. So P of F1 is a Gaussian because it's closed under marginalization. And so for P of F2, comma F1 to be Gaussian, P of F2 given F1 must also be Gaussian. So it's this weird property that the likelihood and the prior combine together to form a Gaussian. It's very unusual. The conditional density is also Gaussian, but the way we find, geometrically, the way we find that conditional density is you can kind of think about this. I don't like using this example because I don't know the politically correct name for Ayers Rock, but you can think about this as being the politically correct name for Ayers Rock, that big rock in Australia. Does anyone know it's Uluru? This is Uluru. That confidently cut the bit before. This is Uluru, the rock in Australia. And if you're stood standing, I don't know what shape Uluru is, because they keep showing like Charles and Diana or William and Kate standing in front of it romantically, just from one side. And so I can only see that one side of Uluru. And so if you're looking down here, that's Uluru sticking up. That's the side you see. And that's the marginal distribution that we saw before. So the probability of heights, even though they're correlated, you can't see that correlation if you just look at the height only. You just see the full width of the distribution. So it's a bit politically incorrect to do the next operation. If you want to condition on one value, you have to cut through Uluru with a big slice. Actually, there's one through the middle of Iceland that you're going to see tomorrow when you do that tour on the Golden Circle. So you have to do one of those transcontinental cuts through Uluru, and then you look at the profile at that point here. And that's what conditioning does. It takes a slice through Uluru, and you get, as a result, you get the sort of the shape, the outline of Uluru. I'm projecting that back up. That's your distribution over F2. I mean, that's the geometric way. I think geometrically, so apologize if you think, well, just show us the bloody maths. But for me, that's the way I tend to think about it, and that's also Gaussian. So these slices through that Gaussian are all Gaussian. And this is, again, that special property. It's because it's this exponentiated quadratic form that this works. It doesn't work with other forms. It wouldn't work with the Laplacian form, because when you do the independent Laplacians, you just get this sort of nasty square shape. Yeah? Sorry, diamond shape. I'm getting it the wrong way around. You get this diamond shape. And the slicing through the diamond shape in any direction doesn't necessarily give you the same object anymore. So it does in this case, which is great. So what we can do is make a prediction. This is our prediction of where we expect F2 to be, our test data. So we've got this covariance. We combine it with our training data, F1, and then we make a prediction about F2, given that. Now, this doesn't work with independent systems, because your prediction, if this was independent, your prediction about F1, F2 wouldn't depend on F1. So that's why I hate IID, because everyone thinks I'm going to model and it's going to be IID. But if that were true, you were only modeling an IID, then you wouldn't be able to make any cross predictions. Of course, what's really going on is your model is the parametric, non-probabilistic part, and that's why you can make predictions. But all models, if you're doing it probabilistically, they're joint models over the data. And I want to express those relationships probabilistically. That's why I do this stuff. I don't do this stuff because I have a fanatical belief in the uncertainty of parameters. I do it because I want to be able to make joint probabilistic predictions over variables. Yeah? I also have a fanatical belief in the distributions over parameters. Okay, and then this is the maths. So the maths in this case is quite fun. It looks a little bit complicated, but in the one-dimensional case it's quite simple. This is the diagonal term of that covariance, which we actually set to 1. So this is the diagonal for the prediction, and the mean is given by the covariance between f1 and f2 divided by that diagonal term. So it's just a down weight of f1. So if we see it, actually, this mean is it's 0.96 divided by 1 times f1. So it's in the negative space, but it's slightly smaller. It's 96% of f1. Yeah? This is what the maths give us. And the variance of this is given by the prior variance. This is the prior variance, which again was 1, minus that 0.96 squared. No, it's about 0.91, mine 2, something like that, divided by 1. So the variance of this is about 0.09, square root of that. And that's what's giving us this variance here. But it's all related to the correlation and the original observation. Yeah? It's Gaussian conditioning that gives us this. And this is the fundamental thing on the prediction of the Gaussian processes, doing it in one dimension. It's a linear weighted sum over the training data, and then this important object here, which gives us the variance. If you do a lot of other things with kernel methods or whatever, you tend to ignore this object here. You do that for very sensible, honorable reasons, and those reasons are that you don't want to make a Gaussian assumption about your data. You just want to make an assumption about how things are correlated, but not to say how it's Gaussian. Well, that's my interpretation of it, which is fine and honorable. But we're prepared to go ahead and say these are Gaussian jointly distributed, which, then might not be. Quite possibly they might not be. So then we get also this variance out here. But that's kind of the most interesting object. That's the object. Whenever you see a Gaussian process taught, back in 2005 or whatever, we were like, why don't people get it? Why don't people get how important the variance is and how useful it is across this range of domain of applications? And nowadays, all Gaussian process talks start with how important the variance is and how useful that's going to be in their Bayesian optimization or in whatever they're doing. They do get it. That's why people are using Gaussian processes. And the reason they didn't get it back then is because we only cared about classification and SVMs and whatever else, and it wasn't so important in that domain. But it's much more important in these Bayesian optimization domains where Gaussian processes are very popular, as an example, and also in the stuff that we do in my group. Now, if we were to look at a correlation between, if we only observed F5, and we hadn't observed, if we want to predict F5, and we've observed F1, the correlation's a lot weaker. It's 0.57. So in this case, now we get the mean of the new distribution is 0.57 times 0.313, so it's slightly negative. But really the big thing is, and this is why it's important, look at the variance now. It's now approximately 1 minus 0.25. So the variance is blown up. So despite there being some predictability according to this model, the variance is so large that it's like, well, I don't really know. That's why we love variances. Because really, you didn't gain much information there. And that's despite this being like a correlation that a lot of people get super excited about. That's statistically significant. This is something that if you got this in your data, they're correlated. But they're not correlated to any degree where you're going to be confident about your prediction. And indeed, the location of the sample in the previous case was in the positive half space. It wasn't even in the same half space. So going back to what the plot looked like, we can see that things are by the time you get to 5 points away, they're very loosely correlated. We know there's some correlation, but it's not actually giving us much in terms of the function. So, and we can do this in a multivariate way. This is the objective of a Gaussian process, is that we work in this domain and we do this in a multivariate way. We can condition on, so we're given F, our observations. Why am I talking about F and not Y? Because I'm talking about the sort of noiseless system. So for me, Y is the system is F plus noise. So here we're just talking about f before the noise is added on. But you can think of f as y if you like. It's all the same equations. So f is dependent, the test data on f is dependent on the training data of f. Now this big object here is, again, just a linear weighted sum of your training data. And this big object here is, again, it's some sort of quadratic form subtracting from your prior. So this is your prior, so if you have no data, this term doesn't exist, and this term doesn't exist, and you just predict your prior. As you get data, this subtracts variance off the posterior as long as the data is in the right position. This is where, so this is the joint covariance over now the training data and the test data. Let me pause there and check if there's any questions.
Does that include both input and output variables?
I haven't said anything about input, have I? Yeah. And I'm not saying how that's happened yet, so we're about to do that. So all I'm saying at the moment is that we're given a covariance k. But remember, what was the form of the covariance before that's over there on the board? K was XX transpose. So K can contain the data, the input variables. So in effect, we build the covariance by looking at our input variables. And this is, so, you know, I'm not very good at maths and stuff. So I have to have simple ways of thinking about processes and measures and all that sort of thing. And my simple way of thinking about these covariance things, they turn out to be these covariance functions, these Mercer kernels. They have this sort of form. So you can define them for any set of 2 points if you know the x. Now what does that mean? Well, it's like a magical way of building a matrix. See, you have to put magical if you don't understand. That's what it means. I don't understand, so it's magical. It's a magical way of building a matrix that I've got these 2 points, and I need a matrix from these 2 points. So I'm going to ask my magical formula. I give it x and x prime, and say, give me the covariance. Well, where does that magical thing come from? Well, what is a matrix itself apart from a magical way of building a matrix where x and x prime are I and j, row and column? So x and x prime are like an index on an infinite covariance. So it's like you've got a matrix building machine, so, which is just coming from this function. So in a normal case, in a Gaussian process, you're moving from this discrete view of Gaussians to this infinite view of Gaussians. What we need to do is now think about a continuous field. As Harvard Rue said yesterday, he would talk about it as a Gaussian random field, which is another way of saying it. And if we think about it as this continuous field, we need to be able to define the covariance between everything. And you know, my view on it is it's the covariance between everything. So we can ask, for example, what's the correlation between the temperature in the Blue Lagoon in Iceland and, I don't know, the temperature at the top of Mount Everest? Well, probably nothing. But it's a question you can ask. And you can ask it for all variables, as long as you can build a covariance function between them. So you can sort of imagine, if the world was all Gaussian, what we could potentially be building is a way of getting a correlation answer between any 2 variables in the world. And if we could do that, and the world were all Gaussian, then we could make these properly probabilistic predictions over everything in the world. Now there's a few flaws in that process, in that the world isn't all Gaussian, and we'd have to design the covariance. So all the open questions in Gaussian processes are, how do you deal with the fact that the world isn't Gaussian and you have to design a covariance? Okay, but this bit's simple, because it's just conditioning. So you're making this one assumption that everything you're interested in the world is jointly Gaussian, and that you've been given a covariance somehow. Other questions? Did I answer that? Sorry, I went beyond as well.
My real question is what we effectively want to do in regression is to from some inputs. So we're trying to work out the correlation between the inputs and the outputs.
Well, no, you think that, but we're actually trying to work out the correlation between the outputs given the inputs. Right. So the regression conditions on the inputs. Yeah. So if we wanted to do that, then we would be doing a joint model, and then we would have to sort of build a covariance over the inputs and the outputs, and that would be more like unsupervised learning. And in fact, Pearson looked at exactly that question. He sort of noticed that if I do linear regression, he said, oh, Galton's regression, blah, blah, blah. But if I regress y against x, I get a different answer than if I regress x against y. And what if I want that answer to be symmetric? And he said, how do I find that? And the answer is, it's the direction of largest variance in the joint covariance of y and x, which is PCA, but he didn't call it PCA. It was just the right algorithm. PCA was invented later for a different reason. It just happens to be the same algorithm. So that's a sort of slightly different thing and is more of an unsupervised learning thing. You're right. If you didn't know which you wanted to predict, if you wanted to predict y from x or x from y, you build a joint model for y and x. And what I don't think he interpreted as this, what Pearson was effectively suggesting is jointly model them as Gaussian, and then the conditioning will be the direction of the principal component. Yeah. But here, we're conditioning on x. So x comes into the model. We don't see it as a probability. We don't have a distribution over it in the model. Anyone else? So to me, that's the difference between supervised and unsupervised. In supervised, I'm conditioning on x, and in unsupervised, I'm jointly modeling x and y. Other questions? It's all clear? Everyone implement Gaussian processes now? Good. Okay, so I like this animation that Philip Hennig came up with. It's supposed to kind of illustrate the sort of samples you can get from this. So we saw one sample before, and what Philip had this idea of is that there's each of these functions actually exists in like an infinite dimensional space. So how are we sampling them? Well, we can't sample the infinite dimensional space, so we're sampling very finely across that infinite dimensional space. So any 2 points close together are very tightly correlated together, so they appear together. So we're sampling these two, we're sampling like 200 values along here. But then I guess Philip was bored of the sort of standard examples we look at, and he sort of said, well, how can I illustrate what the function does? And he's got a really nice talk, which is also available online from a couple of locations, where he sort of shows all these different covariances and what these things look like. And the way that the idea he came up with is let's show a great circle around the sample space. So we pick a location in the sample space, and then we take a circle of equal probability and return to that location. So these are all valid. So what we do is we're taking a sample from a Gaussian process, and then we're taking a tour of Gaussian processville and returning to that sample, a circular tour. And that's what these sort of samples look like. And this is the machine we use for creating the covariance. But the nice thing is that we don't have to just use this one machine. There's lots of ways of creating a covariance. So because the sum of two functions that are both Gaussians is also Gaussian, with a covariance that's the sum of those covariances, if you want to add two Gaussian processes together, you get a new Gaussian process. And the covariance of that new process has a covariance which is equal to the sum of the two underlying processes. This product is harder to understand, but it turns out the product of two covariances is also a covariance function. So what is a valid covariance function? Well, it has to always lead to positive definite matrices. So it's this magical way of generating these matrices, but those matrices are covariances, so they have to be positive definite. So anything's a valid covariance function as long as it gives you a positive definite matrix for any of the inputs you put in. And people have looked at, and it's all mostly done in the kernel methods literature, but people have looked at what happens if you put two graph structures in, or two strings. So x doesn't need to be a continuous real-valued vector. It often is.
Sorry to interrupt you, but I was just confused about this tour that you said about these covariance functions.
Oh, the Philip tour. Yeah, I probably didn't explain very well this one.
Given one sample, how do you come up with one that is close so that you have this smooth?
Right. So so we take one sample. So it's like the sample is like landing somewhere on the Earth, and the Earth is infinite dimensional. But let's just think about the Earth. And then choosing a direction in the Earth, which is a great circle, and following that great circle around and then coming back to your starting location in probability space. So the Earth is like a contour of probability in this infinite dimensional space. And you're choosing a function in the infinite dimensional space, and then you're choosing a great circle to tour that infinite dimensional space to go around.
You're walking along the contour of the...
You're walking, so it's like you might land on the equator, and that's a great circle, or any of the lines of, which way around? Longitude and latitude. One isn't a great circle and the other one is. The one that is a great circle, you land anywhere, or like you land in Greenwich and you walk to the North Pole and round. You're doing that tour. So your sample lands you in Greenwich and then you go around the North Pole. So it's got to be a great, and then you're visualizing that walk as functions. Philip's got a paper about it online about how he generates these things, and he does a lot more with it. I just think it looks funky. what was I saying? Something about Gaussian processes, I suspect. Anyway, they're really good. Okay, so if f of x is a Gaussian process and g of x is a deterministic function, this is another funky thing that comes out. The result of multiplying the two together, it doesn't work if g of x is a Gaussian process, because that's Gaussian multiplying by Gaussian in a sample space, not in a distribution space, and that leads to non-Gaussian. But if it's deterministic, you just get this new covariance, and that's quite nice as well. And then there's things you can do. What you can do, remember before we had this marginal likelihood in this form here, which said that, so we started all this with a linear model, and then we said xx transpose plus sigma squared I is our covariance. And then I said, yeah, but we could make that the basis set, phi. And this is what justifies the idea of it being a basis. So when you make this the basis set, this is the general field of generalized linear models, where these are your basis functions, and this is the covariance function for it. But the kernel trick is to say, let's have infinite basis functions, which means that this guy inside here, this is an n by p, so there's a multiplication going in across p by n matrix. You're taking that p to be infinity. And that's what's going on with these models. That's what makes them so powerful, actually, is that you end up with infinite features. Now, the standard Gaussian covariance here, this guy, the exponentiated quadratic, can be derived by thinking of those features as those little RBF features we had earlier, but having infinite of them across the real line. But if you decide to have little sigmoidal-like features like people do in neural networks, you get this covariance instead. So you can derive a covariance. Chris Williams did this back in '96, and this is a covariance that arrives from that. And the functions look different, right? They have this sort of saturating behavior, and the location of the width of this saturating behavior is dependent on this parameter b. I'm not going to go into the details, but I've kept it kind of small here. And how much they wiggle is dependent on this parameter w. So these covariance functions, they have parameters. This is the linear one. This is just the one we had before. So you can see it goes up quadratically. At the center, it's 0. It goes up quadratically either side. And if you sample from this, you just get these linear functions. It's a really weird thing to do, to go to all the effort of building this object here and then sample from it. It's kind of a bit weird. You then take a Gaussian sample from this object in Octave. It will complain a little bit. You know, it'll say, oh, that's not quite positive definite. But if you add a little bit of noise along the diagonal, and what you'll find is you're sampling a line. The reason it will complain a bit is because these are degenerate covariances. They're not really invertible. They're rank 1.
Slightly orthogonal question, but would it be accurate to think of this as max entropy learning and the covariance is what is the moment you try to match, or is that just a bad way of thinking about it?
I don't know if I like max entropy, but I don't know if it's a good way of thinking about probabilistic modeling. I think Jane's suggested it as a way of generating probability distributions, and I've used it in the case where I found it hard to think of what the likelihood should be, because the moments I was interested were squared distances. So I wanted to fit squared distances, and so I fixed those things as moments, and then that told me what the distribution should be in the input to those distances. But it is true that maximum entropy does lead to Gaussian models. It would be difficult, though, to see it exactly like that, because it's actually an interesting point, because it raises something I haven't emphasized. If we were just fitting, there's something odd going here. If we were fitting it as a max entropy model, and we wanted to take all these observed second moments and have the distribution match them, then we would find that the answer was, under the maximum entropy system, that the covariance k should equal y transpose, where y is an n by 1. So this is an n by n matrix, but it's rank 1. Because in effect, in a Gaussian process, we observe one sample very often. We might observe multiple samples, but that's kind of like multitask learning. But in the way I'm describing it, we observe one sample from this distribution within which all is correlated. And if we were saying we wanted to match the moments of the probability distribution to the moments of that sample, we would be using very badly estimated moments. Basically, in effect, we'd have to assume the mean was 0 or something, and then this is the second moment. But it's still a bad fit. But we don't do that. K is not allowed to just equal y transpose, because K is parameterized. This is what makes the fit difficult. So we can change k, but we can only change k by changing its parameters, and that moves all the elements of k together. So really, k just has a couple of parameters for the examples we've seen. And well, if there's time, I'll briefly talk about how we do maximum likelihood fits of those, or why we can do maximum likelihood fits. So I started out thinking the answer to your question was yes, but as I answered it, I think no. But you know, maybe I'm not sure. It was just a random walk around the potential answer space. But was it helpful? Okay, good. So that's linear regression. This is looks like a Laplacian. It's actually the covariance underpinning the OU process, which is a Gauss-Markov process. So this is the sort of thing you might be more used to expecting to see coming from Gaussian processes, these discontinuous paths. This is the type of path that might underlie a Kalman filter. So Kalman filters don't have these smoothness assumptions because they have Markov assumptions. So this process here is the unique Gaussian process that is also Markov and is stationary. And this Markovian structure means that they're non-differentiable paths. You might think, what do you mean Kalman filters are non-differentiable paths? They absolutely are. Ask Arno, he's an expert. It's just you only visualize the mean. The expected path is continuous, and you tend to visualize that. But if you look at the sample paths underlying it, they're discontinuous. So if you don't believe in a discontinuous sample path, this is for a vanilla Kalman filter, you can expand them with state space models and fix this up. But if you don't believe in these sort of random walk sample paths, you should potentially question whether you should use a Kalman filter and perhaps not go to something more like a state space model. This is a pure Markov process a la sort of it's just this object here, and it's sort of a non-stationary Gauss-Markov process, Brownian motion, where you started at 0 here and you just wiggle around out. So there's a bunch of things. This is a popular covariance, which is the return covariance, so that exponentially quadratic covariance is infinitely differentiable. That means it's a prior over functions that are infinitely smooth, which is the opposite of that Markov thing, because they're not even differentiable. But it may be a bit too strong to assume that. And these return class of covariances allow us to sort of filter between that. They allow us to have functions that are a few times differentiable. And the return 5/2 is twice differentiable. Well, it would look, the length scale I've made purposefully large to try and give the impression of these sort of, it's got this less smoothness than the exponentiated quadratic covariance, which is often useful in practice when your data is very densely together, because you can get degeneracies in the exponentiated quadratic. So that's a cool covariance. This is the covariance you get out of doing this thing I wrote over here. So with these 3 basis functions I had earlier, just laid across the line, but the problem with it is that these are the sort of functions you sample. As soon as you move away from those basis functions, you predict 0, regardless of the data. So that's a bad thing to do. This is why we like Gaussian processes, because Gaussian processes have this interpretation of the same thing, but infinite basis functions across the real line. So wherever you go, you get these variances. And that pops out when we start doing things like interpolation. So remember the conditioning I said before. I said, well, you have the covariance, and you get some inputs, and then you make some predictions. Well, this is what you get if you combine 2 input observations, so noise-free, no noise, with the Gaussian process. So this is the marginal predictive variance, is the mean and the margin of the posterior prediction, what we're seeing here. Now, there was this sort of discussion, I had a little discussion with Mike Jordan about error bars at the end of his talk, and so I suppose I should emphasize what these error bars mean. Error bars can mean different things. In these probabilistic models, they're error bars that are arising from the fact that you can't determine where the function goes outside the region of the function. So in this case, there's no noise. So there's no uncertainty arising from the noise. They're going right through these points here. But you can't actually determine where this function must go. It's allowed to wiggle up and down. So these error bars are coming from the fact that that function might wiggle up and down. And as we add data, those error bars will tend to collapse. Even, this is this exponentiated quadratic covariance, even to the point where they look degenerate. And this is the problem with the exponentiated quadratic. This phenomena here is very similar to Nyquist's samplings theorem. That if you Nyquist, all signal processing is based on band-limited signals. Band-limited signals are also Gaussian processes. They're just Gaussian processes with a really stupid covariance function because they don't allow frequencies above a certain location. So you shouldn't use it, but all signal processing is based on it. This covariance function has part of that same stupidity in it because it's based on a Gaussian filter in Fourier space. You can sort of show that. I haven't given the details. So it believes very strongly that high-frequency things don't exist. That's what gives it its infinite smoothness. So although you can't prove that this is degenerate, you get a similar effect. It's sort of collapsing very confidently around this line. So if we made a new observation that was just off this line either side, it would be very angry. And when it gets angry, the numerics collapse because it doesn't have any support. I mean, it does. It's a Gaussian process that provably has support everywhere across the real line. But that support is so unlikely. It's collapsing in a quadratic fashion that when you try and fit data which doesn't fit this, you get all sorts of numerical problems in that linear algebra, which are a sign of modeling problems. Okay, so you can add noise and do the same thing, and that's very trivial. So I'm rushing a bit through this bit. This object here is the model. That's the thing I've been trying to emphasize. Can someone point out in this object where the prior is and where the likelihood is? They're hidden. In fact, it's not even potentially clear where the prior was. You can't actually, once you've got the model, say what the prior and likelihood was. There's a few different ways of getting to this likelihood, potentially. But this is the object of importance. That's what I've been trying to persuade you. This is the thing that's telling you how these things correlate. There's other ways of getting here, these state space models, Kalman filters, which you might prefer because of certain interpretability things. But I really think it's informative to write down what this model is and what it's saying about your data, because it is the joint model over your training and test data. So we just expand it. That's just showing the training data, but we just expand it out in that block form to include the test data. What I want to show you is what happens when you do maximum likelihood. So we're going full circle. Now we're going to do maximum likelihood on the parameters of this model. And those parameters are in K. So again, we're going to do log likelihoods, just like Gauss showed for least squares. But it's all a little bit different now, because the data appears in this funny way. There's no sort of mean going on. It's all a bit strange. So I just want to have a look at these terms and show how you do have something that looks like these traditional models. So in a lot of regularization theory, you'll say, this is a data fit term and this is a regularization term. But it won't quite look like this. But this is a data fit term and this is a regularization term. Normally in those models, you have some sort of sum over n. But here you've got this weird inner product, quadratic inner product, sum over n containing your data. But here you've got this weird quadratic inner product. So let's think about those. Now you see why I like this representation here. I'm just trying to draw that covariance in 2 dimensions with a single circle. And this is the underlying basis which appears inside here. It's just a rotated independent basis. We can always rotate it to be axis aligned regardless of dimensionality. So that's the representation I'm going to want to use for this part. And what I want to show is, okay, so this log determinant term is only dependent on this guy here, lambda 1 and lambda 2. So if I have lambda 1 as one basis here, this basis is rotatable, and lambda 2 on this basis here, and I multiply lambda 1 by lambda 2, it gives me the determinant of lambda, this matrix, okay? And that also gives me that area. So that area is given by the determinant of lambda. If I add another dimension, this determinant is given by lambda 1, lambda 2, lambda 3. So it's just a volume. So this determinant term is a volume. Now if you rotate it inside here, and notice I don't have it, I'm just rotating that axis, right? I don't have the full covariance here, I'm just rotating the basis. The determinant of that is still lambda 1 times lambda 2, okay? So under rotation, this volume doesn't change. So it took me ages to find that out because no one taught it to me. I was very deprived. But apparently determinants are volumes. How many people knew that? That's good, okay. So I was only within the half of you. So determinants are volumes. So this is a log volume. Now why is it squared? Well, this isn't quite the log determinant, this object is the square root of the log determinant, but the square root's going on inside, and that's dangerous because there's nothing to stop lambda 2 being negative. Yeah? So if you square this determinant, then that stops it being negative. But if you look in a Gaussian, you both square it and then you square root it. That half there, oh, I missed it. Oh, dear. Should be there. That half there is coming from there. So you square it and square root it, and you're just getting the volume on which the Gaussian sits. So that's the capacity. That's like the size of this covariance. It's volume in some sense. Or it's not so much the volume, not so much the volume of the Gaussian itself. It's sort of, I don't know, the volume of the area it's sitting on, the bits of stuff that sit under it, which is why it appears in entropy as well, because it's somehow the count of the things the Gaussian can represent. The data fit. Okay, this is how to think of the data fit here. So the data fit is a quadratic surface in y1 and y2. So if I've got a data point here, the closer it is to 0, the better my data fit. There's no mean in this. This is 0, 0. You're used to means. The mean doesn't exist when you're doing this data fit. So how can we deal with this data fit? Well, we can do two things. We can blow up lambda 1 and lambda 2, and that would pull this point closer to 0. But if we do that, we would pay a penalty on the volume. We blow up the volume as well. So another thing we could try and do is maybe rotate it and align it with that data point. Now by rotating, this point is dropping into this contour here. And what this is saying is if y1 and y2 are correlated, try and twist the Gaussian process around to make things correlated. Now the model can do that potentially by changing the bandwidth parameter if 2 points are close. Yeah? But if 2 points are far away and correlated, and it's getting a lot of effort out, but in between they're not correlated, which goes all the way back to the function here. So thinking about the function like this, as far as the model's concerned, this was our sample, right? And we're looking at these things here. They were strongly correlated. This is strongly correlated with F1 too, and this is strongly correlated with F1 as well. So to get the data fit good, it would like to bring that one, and that one to be correlated. But by doing that, it would also have to correlate this one by changing its bandwidth term. So it can change the scale of the correlation. But what it can do is get this one correlated by making sure the bandwidth is such that the correlation is matching in this local region. And it will match in this local region here. So it can get this data fit. I mean, it's more complicated. I'm trying to get across the idea that it's more complicated than the figure shows, but it can get the data fit by changing the bandwidth around. It could also get it by blowing things up, but if it blows things up, it pays a penalty. If it just does these sort of rotation-like operations, it wouldn't. So it's got some sort of path of things to deal with. So here's a little data set, and what I'm showing you as I go through the data set is how that capacity term and the data fit term vary. So the capacity term in blue, so I'm looking at an error here, so it's a negative log likelihood, so I'm trying to get small. As we go along, the capacity term monotonically increases and the data fit term monotonically decreases. And the two add together to give us the log likelihood, which has a minima here. And since I sampled the data from a Gaussian process, that actually coincides with the correct value. Of course, the true value is unlikely to be right there. It's probably one side or the other, but I'm only showing you discrete points. So this is where the capacity control comes in. If you use the kernel method, you think, well, how do you find the kernel parameters? And I'll get so sick of people reviewing my stuff and then saying, but how do you find the kernel parameters? Because for a Gaussian process, it's just maximum likelihood. That's like telling people, how do you find the kernel parameters when you're fitting the parameters when you fit a logistic regression? Okay, there's potential problems with maximum likelihood, but basically we do have approaches to finding the parameters. So I'll skip that bit, which is an example. It's not always a good idea to do maximum likelihood. Sometimes you want to do Bayesian inference at this level, but I won't go into that for now because we're coming to the end, so I think I should just go back to questions. Okay, so any questions?
So supposing I'm thinking about whether my underlying function is differentiable once, twice, infinitely many times, and I only have noisy data, how would I ever really verify that it's...
Yeah, no, I think that's really interesting. And in fact, that goes into... So sometimes you see people adding return covariances to return covariances to return covariances. And I have a philosophical question, does it matter? once you've added one Matern covariance, you've actually made things only twice differentiable. So for your other object, you might as well use an exponentiated quadratic because you add the non-differentiability twice, don't you? I don't know. That's my kind of thought on it. I think what can happen is, I mean, if it's, I don't know. It would be perhaps as if you're getting sort of low noise, would be my guess. And you have very finely sampled functions, you might end up being able to characterize the noise variance very well and effectively know what the underlying function must look like despite the noise and believe it's, I don't know, you might still know the spectrum. I guess if you think in a Fourier space, is it right to think in a...
You seem to be getting there, as you said, you wouldn't expect a point off that line now.
Yeah, but if you added noise, you might expect a point off that. And so very often people deal with this problem with the exponential quadratic just with what they call a nugget term, a small noise term, to fix that. But it's, I don't know, I don't really know what the best thing to do is there. There actually might be other people in the room who have thoughts about it, like Arno behind you has worked with these type of models, and I don't know. It may be unidentifiable. The smoothness is difficult to identify in the base case, certainly in high dimensions. So a lot of these issues only arise when you've got highly sampled data in low dimensional input space, because effectively you're trying to estimate a derivative. So in order to estimate a derivative, you need points that are close together relative to that length scale. So yeah, I think it's a difficult issue. There are certainly situations where it's revealed there's a flaw in your model that you've assumed things to be overly smooth. But I don't know whether you can identify better whether it's, I mean, you should try and look at the marginal likelihood and maybe it's better. That would be an interesting experiment to try, actually. See, sample from that actual process and see at what point does the marginal likelihood give you, there must be some point at which the marginal likelihood allows you to distinguish between, say, a Matern 5-2 plus low noise or a exponentiated quadratic plus sort of higher noise or something. It must happen at some point, I would guess. It'd be an interesting experiment.
Yeah, I want to explain again what is the difference between multivariate Gaussian and the Gaussian process.
It's just continuous indexing. So, I mean, I'm very unsophisticated in my thinking, which is why it didn't sound like there's much difference, because I don't think there is. But there is in terms of a lot of the theory. It's a multivariate Gaussian is basically, we've got, I don't know, 5 pens, and we've only got those 5 pens, and we talk about covariances about the color of the pens or something. We say these two are strongly correlated because they're black, and these two are less correlated because they're green and black. But we only are ever dealing with these 5 pens. The Gaussian process is the case where someone keeps giving you extra stuff, and you want a model that's valid when that pen's missing. So they keep giving you new information, but every time they give you something new, in this case you only need to just, your model can store sort of order 5 squared parameters to specify the covariance. Here, every time we get a new pen, we might need a new covariance value. And so we need a way of generating the covariance for that. And that's what the Gaussian process sort of gives us. So it's a generalization where the covariance matrix is being created by this function.
Yeah. So my question concerns that, for example, if our input is not a continuous space, for example, in biology we have this SNP data which reflects the discrete, or the mutation data which reflects the binary inputs. So in that case, what would be the good covariance matrix, covariance functions which can be used in this scenario?
So for SNP data, we've just used this linear thing quite often. In fact, we use that for so-called genetic background modeling. We take the inner product of the covariance. Discrete binary data like that type is often, you don't have to be so complicated over the covariance matrix, because, for example, there's kind of no difference between, for that sort of binary data of the SNP type, I don't think there's much difference between using the linear covariance and the exponential quadratic. I may be getting confused with that and other discrete data. But I don't think it's not really a problem to define the covariance for discrete inputs. you just do the same job. You just need a function that takes discrete inputs and gives you a positive definite output. A much harder thing is what if your output is discrete? And then it's going to be non-Gaussian, sort of by definition. And some of the things I haven't talked about are the limitations of Gaussian processes. And that's one of them, that you now need to do something to map it back to being something that looks Gaussian. But I mean, I haven't done lots of work on discrete, but yeah, as I say, for SNP data, we've just used that inner product covariance quite simply. And that's really, in the model, that's a model we use called Panama, that Niccolo Fusi with Oliver Stagel, where we used exactly SNP data as a covariance term to deal with genetic background, and that seemed to work quite nicely. But there could be other ways of doing it too. I mean, as far as covariance functions goes, the limit is kind of your imagination. That's one of the creative areas of, so I guess for a lot of Bayesian modeling, the creative area is how to do the sampling, how to do the inference. And for Gaussian processes, I'd say a lot of the creative area is how to build an interesting covariance function that respects your beliefs. I mean, beyond the non-Gaussian, there's the bit about how to deal with non-Gaussianity, but let's assume the world was Gaussian, and then it's all about creating covariance functions. And well, we've had a lot of fun doing that in our groups, and I'm sure you could all have a lot of fun doing that too. Other questions?
How do you deal with the situation when the gain grows very large?
The dimensionality, yeah, that's a pig. Yeah, so actually I have a couple of talks online about how we're doing with that, and also from the Gaussian process summer schools, which reminds me, I have to advertise now. If you like that and you would like to hear more, so we're running this series of Gaussian process summer schools where we go into much more detail. So the bit I've shown you is really like my first lecture from that school, and we do I don't know, about probably 18 or 20 hours of lectures on Gaussian processes. And one of the things we look at is how to deal with, yes, because thank you, I didn't point it out, and I should have done, but I was concerned about time, but the inference is order n cubed due to matrix inverse, which we tend to do by Koleski. Now there's some really cool techniques. Arno Solens here is doing some of them with these state space variables for dealing with temporal data that destroy that. We've got this paper on which James Hensman came up with this idea, who works with us in Sheffield, on doing Gaussian processes for big data, where we can do millions of data, but it requires approximations. And the nature of the approximations that we're using for that are low-rank approximations to the covariance. Arno, with Simo Saka, his supervisor, is using these state space representations of Gaussian processes. A little bit related to what Harvard Rue was saying yesterday about how you can discretize the continuous spatial models and get things very efficient. That's another way of doing it across a random field. That's a sort of discretization where you get the Markov property back and you get particular structures in the precision matrix which you effectively exploit. I think, and one thing I would say is that's also signal processing is doing a lot. You know, the bandwidth limitation also means that you can do very large data. Obviously, they fit extremely large data, gigahertz sampling. So this is one thing that I didn't emphasize today, but I like to emphasize, is the separation between model and algorithm. All those things we've talked about, Kalman filter, state space models, Gaussian Markov random fields, signal processing, the model is a Gaussian process. But the full general model has this nasty order n cubed inference. There are specific cases where it's not there, where you can be back at k squared n or something like that. And that's the algorithm though. But one thing that gets lost is when you find a successful algorithm, everyone's like, great, this is how we do it with this algorithm, this algorithm, this algorithm. And then they kill all these problem sets fall down, and they forget what the original model was. And they never go back and say what the original model was. And nowadays we have much greater technologies, and I hope we've made some innovations mathematically. We can revisit algorithms that were not usable before and do much more interesting models. And a lot of that, what machine learning is doing is actually going back to the basic models. We're not inventing any of this stuff, but perhaps taking a fresh look at things like Gaussian processes and coming up with new approximations. So that wasn't quite your question, but sort of. We're probably going over time. Sammy, you can shut me up whenever you like. But just check if there's any other questions, because if you guys want me to shut up, don't ask a question. There's always one bastard, he's asked a question. Okay, so that seems that we've run out of questions, but I'll be here now, so if you've got anything specific you wanted to ask me. I appreciate I sort of lightning went through. I wanted to get something in about Gaussian processes, but what I've tried to tell you about is my philosophy of machine learning, which doesn't need to be done with Gaussian processes. It's just uncertainty. You are going to hear loads about how you can do machine learning with uncertainty from the other speakers, and you will also hear about optimization, submodular functions, and all these other ways of doing things. So at one point I said, that's an error function, and if you follow that route, you get objective functions and all sorts. And I kind of dismissed 2/3 of machine learning and didn't talk about it anymore. So that was missing from my What is Machine Learning talk, but there's loads of cool stuff going on in there. All these lasso type approaches, all that sort of thing, very interesting, but didn't fit within sort of my model of doing things, so I left it out. But that's it. Thank you.